I'm going to talk today about traces of cross-class structure which pervade deep learning spectra. So recently there was a small boom, or a boomlet, if you will, of different researchers measuring deep net spectra, meaning eigenvalues of different quantities in deep learning. And here you can see a small collage of all the different measurements which were made in the last year. And today I'm going to start by looking at some of these measurements that were made and what led to this boomlet to emerge, to erupt. I'm then going to notice how there's certain intriguing spectral patterns that you can see in all the different measurements that were made. And then I'll raise an open question of what is causing all of these spectral patterns which are seen everywhere to appear. I will explain what is causing this spectral pattern through something which is called a meta pattern. And I will explain what is causing this meta pattern through a certain structure that exists in the cross-entropy laws. OK, so let's begin by talking about the earliest measurement in the literature of eigenvalues of a certain quantity associated with deep learning. So in 2012, LeCun and co-authors measured the eigenvalues, or the spectrum, of the Hessian of a deep net. So what is the Hessian of a deep net? It's simply the second derivative of the laws with respect to the parameters of the model. So it's essentially a matrix of size parameters by parameters. And they showed the eigenvalues in a form of a histogram, which you can see here on the left. And so the x-axis are the eigenvalues, and the y-axis is simply the number of eigenvalues that fall in a certain bin.
I'm so sorry.
Wow. And what happened as a result is that, was that 2.5? Sounded kind of similar. And what happened as a result is that people made other measurements following LeCun's work. So in 2014, Dauphine and co-authors made the measurement on the top right, which is another form of a histogram. And in the bottom right, you can see another form of measurements of eigenvalues of Hessians. Now, what's important to understand about these measurements that were made is that the measurements by Dauphine were on MNIST and CIFAR10, downsampled to 10 by 10 pixels. And these data sets are originally of size 28 by 28 or 32 by 32. So that's a considerable amount of downsampling. And the measurements by Sagun and co-authors were done on 100-dimensional Gaussian mixture model synthetic data and on architectures which had a single hidden layer. And they had 70 hidden units only. And so these are very small architectures, and these are essentially what? Oh, 1 second. 1 second, sir. There seems to be an issue. Oh, no. Sorry. 1 second. I think I have the wrong presentation. Oops. 1 second. Sorry. Yes. OK, that's the correct one. Must say you should have the correct one. Sorry. And so what's important to understand about these measurements is that these are very small-scale toy problems. So it's the year 2019 of our Lord. And people no longer use 5,000 parameter neural networks. People are using tens of millions parameters, billions parameters. And what happened in the last year, in 2019, is that we saw a very gigantic increase in the scale and ambition of the measurements that were made in the literature. And people started measuring the eigenvalues of very deep networks, very large networks. And you can trace that gigantic increase in ambition to a set of algorithms that were popular in the quantum physics literature in the 1970s, which explain how you can approximate efficiently the spectra of large linear operators. And in 2018, I wrote a paper that shows how you can leverage these ideas to approximate the spectra of the DeepNet Haitians. And so here are the measurements that you can see that appear in that work. So I'm showing you here the spectra of VGG11, which is an architecture with 28 million parameters. And each one of these rows corresponds to a different canonical data set. So MNIST, Fashion MNIST, CIFAR10. And each one of these subplots shows on the x-axis the eigenvalues, and on the y-axis the log density of the eigenvalues, which you can think of as the count of eigenvalues that fall in that bin, intuitively. Now, as a result of this new ability to measure eigenvalues of very large neural nets, there was a boomlet in the study of DeepNet spectra. And I'm showing you here, to be honest, a partial list of all the different papers that made measurements. First, they made measurements of the Haitian, and later they started measuring other quantities, including the Fisher, the gradients, and so on. Now, I'm coloring here in red, in green, all the papers which have made measurements in the last year only. So you can see how trendy this is. And what's interesting about all of these papers, and you can count probably more than 20 of them, is that all of them observe a certain structure, which is called a bulk and outlier structure. And what's even more interesting is that it seems like none of them actually notice that. So there's many, many different papers in the literature. A certain phenomenon appears in all of them, but no one's talking about it. So if I go back to the, yes?
Some of them make comments.
Some of them make comments, yes. But maybe not realizing how prevalent the structure is across different fundamental quantities. So if I go back to the measurements I showed you of the spectrum of the Haitian, if you look closely at these measurements, notice how there is, in all cases, a set of eigenvalues which are significantly larger than the rest of the eigenvalues. And so I'm going to call these outlier eigenvalues outliers. And there's also a set of eigenvalues which are essentially clumped together in the histogram to form what is called a bulk. So you have a bulk and outlier structure. And it appears in all of these figures that I'm showing here. Now, if you go to other papers, so for instance, Li et al. In 2019 decided to measure the Fisher information matrix. What is the Fisher information matrix? Does anyone know? Since this is educational course, maybe I can quiz you guys. Points in the final grade for the person who knows what is the exact definition. No, you don't get points. Anyone? Mm-hmm. Yes, yes. Yeah. Except that if you are using a cross-entropy loss, then you would have a second derivative of the loss with respect to the predictions in the middle of this outer product. So just to repeat the answer is that the Fisher information matrix is the outer product of the gradients of the loss with respect to the parameters of the model. Now, a second question, what is the relation between the Fisher information matrix and the NTK? Again, for bonus points in the final grade. Anyone? Does anyone know? No, Dave. Okay. So does anyone remember the definition of the NTK? Has anyone been here during the lecture of the NTK? I'm sure every single person I see here has been in the lecture of the NTK. So, okay, so just to repeat the answer of the Fisher information, which I'm going to denote by G in my lecture, is the summation of the outer product of the derivative of the loss with respect to the parameters. So this is the gradient, and you're essentially doing the gradient outer product, which is a matrix of size parameters by parameters, right? And this is a summation over the different samples that you have in your data set. Now, what is the definition of the NTK? The definition of the NTK is it's a matrix of essentially d loss to d theta. So, by the way, you could write this, as simply d loss to d theta times d loss to d theta, where, okay, never mind. Then tk at place ij would be the derivative of the loss of the ith example, inner product with the derivative of the loss of the jth example. So again, what is the relation between these two matrices? One is the second moment of these gradients, and the other one is the gram of the gradients. So this NTK matrix would be the size of sample size by sample size. So in RMT, we would call these companion matrices. Maybe beyond RMT, we call these companion matrices as well. Question?
So what you can say is they have the same non-zero eigenvalue.
Yeah. Okay. Educational part is over. So in the Fisher, so here you can see the spectrum of the Fisher information. And if you look closely at these measurements, you can see how there's, again, a set of eigenvalues which are emergent. You can see how there's, again, a bulk in all the different measurements. And you can see in the middle, there seems to be something like more outliers. So in this case, you can see there's 3 different components in the spectrum. Here's another interesting paper. It's by Guri et al. And co-authors. And what they notice is a very interesting phenomenon about the gradients of SGD. So they notice that the gradients of SGD, after a short period of training, are apparently spanned by some low-dimensional subspace. And moreover, this small-dimensional subspace is essentially the same subspace spanned by the top eigenvectors of the Hessian. What does this mean? It means that if one were to make measurements of the spectrum of the gradients, then you would see essentially some low-dimensional structure that's hidden in that spectrum. So again, outliers plus bulk. And this also suggests that there seems to be some relations between gradients and Hessian. Here's another measurement. So this is of a paper by Verma, Bengio, and co-authors. In this paper, they were interested in proposing a regularization technique, which is called mix-up. Doesn't matter what it does. But what is important is that as part of their paper, they made measurements of the spectrum of the features post-ReLU in different layers. And they compare the spectrum once they use their regularization technique and once they don't use it. And if you look closely at their measurements, you can see how there is a single outlier which is separated from a bulk in all of their measurements. And what their point was is that it seems like their regularization technique is forcing the representation to be lower rank. Here's another example. So Martin and Mahoney actually gave a lecture here at Stanford, and they measured the spectrum or the singular values of the different weights in the different layers. Again, if you look closely, you can see there's a bulk and there's a set of outliers. And so at this point, you should be wondering to yourself, why are so many researchers measuring all of these deep net spectra? Why are they interested in the eigenvalues of these quantities? And the reason is because these are fundamental quantities that we should understand. The Hessian represents the local curvature during training. And by better understanding it, you could potentially better understand what does the speed of SGD depend on. And we know from classical statistics that the Fisher information is related to generalization. And so by understanding the properties of the Fisher information, you would be able to understand something about how greedy is the network in terms of the data it requires. And so people would like to understand the spectra of these objects because these objects are important and fundamental. And there's a set of open questions that arise from all of these measurements. For instance, what is causing all of these outliers to appear? How many outliers are we seeing? Are these outliers signal or are they noise? If they're a signal, if they're important, how can we leverage them to make our networks better, faster, stronger? And why? What? And why? Huh? And why are these measurements and structures so ubiquitous? So what I am going to show you today is that there is a single meta pattern that covers all the different structures that were observed in the literature. And this meta pattern looks as follows. You have, again, a plot of the eigenvalues on the x-axis versus the density on the y-axis. And you can see how there is a single outlier eigenvalue, which is separated from the rest. Then you can see how there's C minus 1 outliers, where C is the number of classes. So if we have 10 classes, it would be 9 outliers. Then we have C times C minus 1 outliers, which is approximately 90 if you have 10 classes. And then we have a bulk. Now you can see how these C times C minus 1 outliers are sometimes clumped together to form a continuous shape. So it's kind of like a mini bulk. Oops. And so you could think of different variations of this meta pattern that are simple to understand. So imagine that some of the outliers could be eaten, engulfed by the bulk. And so you might see instead of C minus 1 outliers, C minus 3 outliers. And you could see that the different patterns are ordered in different fashions. So the mini bulk could be on the left of the main bulk, and so on. And all of these different variations cover all the different measurements that were observed in the literature. Now the question is, what is causing this meta pattern to emerge? Why do we see this meta pattern? And the answer lies in the function that we're optimizing. So we're minimizing the cross-entropy loss. What is the cross-entropy loss? Imagine that you have a data set of size n examples per class times C classes. So in C for 10, it would be like n equal to 5,000, C equal to 10. The cross-entropy loss is a summation of n times C terms, where the summation is over 3 indices, I, C, and C prime. And you have YICC prime times log PICC prime. What is YICC prime? YIC is the target of the ith example in the Cth class. And so it is a C-dimensional vector. And C prime is simply picking a certain entry from this target vector. So YICC prime is a scalar. PICC prime is the probability that is predicted for the ith example in the Cth class to belong to class C prime. So essentially, C and C prime are a pair of indexes that you could think of them as encoding your confusion matrix. Now, there's a key observation, which is each one of your examples in your data set has to be confronted with all the possible classes it could be confused as. And so there is a set of C terms that correspond to these different confusing classes. And I'm going to call C prime in what follows a cross-entropy class, or in short, a cross-class. Cross-class, cross-class. So what happens is that this 3-index structure appears in different quantities because it is inherited to these different quantities. So for instance, you could think of the gradients of SGD. What is the gradient? The gradient is the derivative of your loss with respect to the parameters in the model. So that's what you can see here. Now imagine that I take the gradient and I change the label not to match the true label of the example. So imagine I take an image of a cat and I label it as a dog, and then I compute the derivative of that loss. Then I get 3 different indexes, which are 3 different quantities I can choose. The example number, which is I, the true class, which is C, and the cross class, which is C prime. And you could have the same type of idea in the backpropagated errors. So does anyone know what are backpropagated errors? Again, back to the educational part. What is the definition of backpropagated errors? Elon looks like it's trivial, too trivial to answer. So maybe you should answer.
No, I wonder if I'm supposed to know what it is.
You are. If you were you in the first lecture? So no, not supposed. So backpropagated errors, imagine you're running the backpropagation algorithm. What is the backpropagation algorithm doing? It's taking the loss at the final layer, and it's computing the derivative of the loss with respect to the different modules in the network. And so you're essentially backpropagating the error to the different modules. And once you have the derivative with respect to a module, you compute the derivative with respect to the parameters using the chain rule, right? So the fundamental process that is happening is the backpropagation of the error throughout the layers. and then the computation of the derivative of that layer with respect to the parameters. In simple expression, what's happening is the derivative of the loss with respect to the output of a layer, which I denote by z. Make sense? And so because this is a derivative, again, you have this 3-index structure. So formally, I'm going to define the cross-class structure as follows. Imagine you have a set of vectors which are denoted by V capital I. Then I say that they exhibit a two-way cross-class structure with replications if the elements can be indexed by 3-tuple I, C, C prime. I is the example or the replication, C is the class, and C prime is the cross-class. And so you can essentially denote these elements by VICC prime. Now, why is any of this important? The importance lies in the following observation. Notice that you can take all of this VICC prime, and for each fixed C and C prime, you can average over the index I. And so as a result, you get C² different cross-class means. You can take these C² cross-class means, and then you can fix the index C and average over C prime. And then you get C-class means. And finally, you can take all of these class means and average over C and get a global mean. So it's just 3 levels of averaging. In the first level, I'm averaging over I. In the second level, I'm averaging over I and C prime. And in the third level, I'm averaging over I, C, and C prime. Why is this important? Because you can take all of these vectors, VICC prime. Elon, you seem like you have a question, but you're too shy to ask.
Yeah, I is the indices goes over the data points.
Yeah, it's the replication or the examples in a certain class, like the first kitten, the second kitten.
The self-path output?
No, V in this case is just a general vector, and V could be, so I'm going to say that V, for example, is the gradient, or V are the backprop errors. V can be any quantity in the deep network, which is a vector. Thanks for the question. That's a good question.
So a family of vectors indexed by subscript called subscript called cross-class.
Yeah. And you can take all of these vectors, VICC prime, and you can form a second moment matrix, which I'm going to call V. And there's a fundamental decomposition of this second moment matrix into a summation of 4 covariance matrices. The first one is just a rank 1 matrix of the global mean. The second one is a between-class covariance, which measures the variation of the class means around the global mean. The third one is the variation of the cross-class means around the class means. And the last one is a variation of the observations around the cross-class means. It's just the composition of variance the same way you would see it in MANOVA. Why is this important? This is important because what I'm going to do is I'm going to show you how the different spectral patterns that appear in the second moment matrix V can be attributed to one of these matrices. The top outlier is going to be due to this matrix. The C-1 outliers are going to be due to this matrix. The C² minus C outliers are going to be due to this matrix. And the bulk is going to be due to this matrix. Now, as Morteza wisely asked, what is V? So V is a general vector. And there could be different instances of this cross-class structure. So you could have, for instance, the features, which I'm denoting by H. You could have the backprop errors, which I'm denoting by delta, or the gradients, which I'm denoting by G. And there's a plethora of different definitions here of different means and covariances and so on. Morteza, you seem uneasy again.
No, I wanted to see the application.
Oh, we'll get to the Haitian. So essentially, yeah, that's a great question. So I'll leave it to a later part of the talk. I can answer now if you want. You allow me to proceed? Okay. So what I'm going to do now is I'm going to define something called a knockout. A knockout is when you take a certain matrix A and you eliminate from it another matrix B. You could have two types of knockouts, a subtraction knockout, which is A minus B, or a projection knockout, which is the projection of B from A. Why is this useful? Because I'm going to do spectral attribution using these knockouts. So I'm going to look at the spectrum of a certain matrix A, and I'm going to look for a certain pattern P that appears in that matrix. So that could be an outlier. And then I'm going to try to see how does the spectrum of A looks like after I knock out B. And so if I see the pattern P in A, but I don't see it in A after B is knocked out, it means that this pattern is attributable to the matrix that was knocked out. So let me give you examples. So on the left here, you can see on the y-axis the log eigenvalue of the spectrum of the second moment of the features. So these are the eigenvalues of the second moment of the features. And these are the eigenvalues of the second moment of the features after I knock out the global mean. So the black line here is the identity line, which means that the eigenvalue does not change its value as a result of the knockout. Notice how most of the eigenvalues are on this identity line, which means they're unaffected by the knockout procedure. There's a single eigenvalue which is above this line. What does it mean that it's above this line? Notice that if I were to project this point and this point onto the y-axis, I would get that there is a very large margin, which means that this eigenvalue is in fact an outlier in the spectrum of H. However, if you project it onto the x-axis, you can see that there's no longer any margin. This means that this eigenvalue is no longer an outlier in the spectrum of H after the global mean is being projected away. What does this mean? It means that by projecting away the global mean, we've managed to eliminate the top outlier. Hence, the top outlier is attributable to the global mean. On the right, I'm keeping track of all the different attributions I'm making. So I attributed the top outlier in the spectrum of the features. Here's another example. So here I'm showing you on the y-axis the spectrum of the features. On the x-axis, it's the spectrum of the features after I eliminate the class means. Notice how there's a set of C outliers which are eliminated by knocking out the class means. This means that these C outliers are attributable to the class means. In the case of the features, there's no C-squared outliers, so I'm just going to write not available. Then I move to the backprop errors. So backprop errors are denoted by delta. Again, it's the same thing. You can see that there's a single outlier which is present in the spectrum of the backpropagated errors, but it does not exist in the spectrum of the backprop errors after I eliminate or knock out the global mean. This means that this top outlier is attributable to the global mean. I see some angry, confused face in the crowd. No? Not angry? Not confused? Question? No question. Question? No question. Here's another example. Here you can see on the y-axis, again, the second moment of the backprop errors. And on the x-axis, you can see the second moment of backprop errors after I eliminate the class means. And again, you can see that these outliers are attributable to the class means. And the final example shows what happens once you compare the spectrum of the backprop errors after you eliminate the class means versus what happens after you eliminate both the class means and the cross-class means. And in this case, you can see how there's a set of C-squared outliers which are eliminated, which means that these C-squared outliers are attributable to the C-squared cross-class means. So essentially, we've managed to attribute the top outlier, the C outliers, and the C-squared outliers in the features and in the backprop errors. Now, we could repeat the same type of ideas for the Fisher information matrix as well. So I could decompose the Fisher information into a second moment. I could define the between-class covariance, the between-cross-class covariance, and so on. And I could make these attributions similarly. So here in the first row, you can see the spectrum of the Fisher information. And in later rows, you can see the spectrum after I knock out different quantities. And you can see how this eliminates different spectral patterns. Now, at this point, here's a question. What is the relation between the spectrum or between the cross-class structure in the features, in the backprop airs, and in the Fisher information matrix? Because we know the cross-class structure appears in all of these cases. So let's consider a very simple scenario where we have a single fully connected layer in between two ReLU layers. So this fully connected layer obtains as input the features H and outputs the, pre-activations Z. Now, the backpropagated airs are essentially the derivatives here with respect to the output of the fully connected layer. It's very easy to show that the gradient of this layer, or the loss with respect to the weights of the fully connected layer, are simply equal to the Kronecker product of the features with the backpropagated airs. Well-known fact. It is also easy to show that the Fisher information is a second moment of these gradients, weighted by some weights. Now you can simply plug the equation at the top of the gradients into this second moment, and you would get that the Fisher information has a certain Kronecker structure in it. And so what this means is that there is a very clear relationship here between the features H, the backpropagated airs delta, and the Fisher information G. And we would like to make this relation more explicit. How can we make that relation more explicit? So here's one suggestion we could do. Imagine that we just assume that the features and the backpropagated airs are independent. And so you can just take this summation and decompose it into the Kronecker of two independent summations. So in 2015, Martins and Gross suggested to do that in their work, which is called KFAC. And that's essentially an approximation to the Fisher information matrix. Another thing that you could do is something which I call class-distinct factorized approximate curvature, or CFAC in short, which essentially approximates the Fisher information as the average over the class conditional second moment of features chroniqued by the class conditional second moment of backprop airs. So it's essentially saying that the Fisher information is the Kronecker of features and backprop airs. You just have to condition everything on the class. Now, here's a comparison between the spectrum of the Fisher information matrix, which is depicted in blue at the top row, and the spectrum of KFAC, which is depicted in orange. So the first thing you can see here is that there is a set of C outliers in the spectrum of G. There is a set of C-squared outliers in the spectrum of G. So here are the C-squared outliers. And you can see how the spectrum of KFAC is completely misaligned with the spectrum of the Fisher information matrix. So essentially, it's a bad approximation. At the bottom, you can see the spectrum of G in blue, the spectrum of CFAC in yellow, class conditional version. And you can see how they almost perfectly align. Now, these are measurements which are done on a single layer, but you could also do them for all the different layers. So here, each and every one of these rows corresponds to a different layer. And you can see how in all of these cases, you get a very nice alignment between the two. What does this mean? It means that you have a certain structure in the spectrum of the features, which is this cross-class structure. And you have the same structure in the backpropagated airs. And what's happening is that the outliers in the features, which are due to class means, are being Kronecker product by the outliers, which are due to class means in backprop airs, to create outliers in the Fisher information matrix, which are due to, again, class means of gradients. So class means of features Kronikered by class means of backprop airs create class means of gradients which create outliers in the Fisher information matrix. That's a very long sentence. And similarly, you could take the outliers in the features, chronicle them with the C-squared outliers in the backprop pairs to create C-squared outliers in the Fisher information matrix. So essentially, we understand the relation between the features, backprop pairs, and the Fisher information matrix. You could go one step further and ask what is the relation between the Fisher information matrix and the Hessian. And it's very easy to show that the Hessian is equal to the Fisher information plus some residual. And here what I'm showing you is the spectrum of each of these terms. So the top row shows the spectrum of the Hessian, where you can see that there's this bulk and a set of outliers. The second row shows the spectrum of the Fisher information, where you can see how these set of outliers appear again approximately at the same locations. And the last row shows the spectrum of the residual, where you cannot see any outliers. So again, what this means is that the outliers which are in the Fisher information are essentially inherited to the Hessian. And so we started by looking at these measurements of the Hessian and noticing that there is a set of outliers and a bulk. And at this point, you should be able to understand that these outliers in the Hessian are created by outliers in the Fisher information, which are created by the Kronecker product of outliers in the features and the outliers in the backprop pairs. I think that Masa got it. Masa, did you get it? Like you were. OK.
Is this a breakout, or is this
Somewhat empirical. So what do you mean by proven?
meaning that you can say that the outliers, like Hessian, are like exact outliers of the feature information?
So it depends what assumptions you start with. Because if your assumptions are, I'm training a network on some data, then it depends on the architecture you're training, right? So I would say it could potentially be proven if you make enough assumptions. I could go as far as claim that it's proven in a very shallow network of 0 hidden layers. So let me show you why I think this cross-class structure is of fundamental importance. So here I'm showing you an alternative visualization of the spectrum of the features using something called a scree plot, or how Morteza calls it. I will not repeat. So you can see on the x-axis an index of an eigenvalue, and on the y-axis the eigenvalue. And in blue, you can see the eigenvalues of the second moment of the features, which again show a bulk, an outlier, which is bigger than the rest, and C-1 outliers. And at this point, we understand that the top outlier is attributable to the global mean. The C-1 outliers are attributable to the C-class means. And the rest is attributable essentially to the within-class covariance. Now, you could take this measurement and you could repeat it as function of depth for the different layers of the network. And then you see the most beautiful phenomenon ever, which is this. So here, each one of these columns is showing the spectrum for a certain layer from 1 to 8. And what you can see is that initially, at the first layer, the outliers, or which are essentially attributable to the class means, are buried inside the bulk. What does this mean? It means that essentially the norm of the class means is too small for them to emerge from the bulk. At a certain point, you can see how these class means emerge from the bulk. They're strong enough to create outliers. And eventually, they separate from the bulk to the point where there's a very large gap. So you can essentially understand that the deeper you go with the network, the stronger the class information compared to the within-class variation. Now, if you were to do only spectral analysis, then you wouldn't be able to see this phenomenon. Why? Because you would just see the blue points that I'm showing you here. And the blue points show that at a certain point, you get a set of outliers emerge from the bulk, but they don't tell you how much are these class means buried inside the bulk at this stage. Now, another phenomenon you can see here is that once you go deeper throughout the layers, the ratio of the eigenvalues of the class mean low-rank structure is becoming closer and closer to 1, which means that the class means are becoming closer and closer to being orthogonal. So there's two separate phenomena. One is the gradual separation of class means from noise, and the other one is the gradual orthogonalization of the class means. Obviously, the most optimal thing you could have is orthogonal class means, right? If class means are orthogonal, it makes classification easier. Now, here's an example of a certain mathematical statement you could make about this cross-class structure. So imagine that we have a very simple canonical classification model where we have a set of class means, which are simply the one-hot vectors, which I'm denoting by EC. Imagine that I take these one-hot vectors and I contaminate them by some white Gaussian noise, and that there is a certain tunable parameter which I'm calling T, which is the signal-to-noise ratio. So the samples are T times the class mean plus some noise. Now imagine that I take this data and I train on it a zero hidden layer neural network, which in the old days we would call multinomial logistic regression. Now imagine that I have a simplifying assumption that the probabilities predicted by this multinomial logistic regression are symmetric. What does it mean, symmetric? It means that if you think of a then classifier would say the same probabilities for all the of a cat being a dog is equal to the probability of a cat being a horse. Just some symmetry assumption. Under this setting, you can actually derive the spectrum of the expected Fisher information and show that the spectrum actually has the same structure that we kept talking about throughout this lecture. So there is a set of C outliers. There is a set of C squared minus 2C secondary outliers. And then there is a bulk. Now, what's cool about this derivation is that it shows what is the magnitude of the outliers compared to the bulk, and what is the magnitude of the mini bulk compared to the bulk, and what does it depend on. And if you look closely, you would be able to see that, as you would expect, the better the network is classifying, in this case the multinomial logistic regression, the more the outliers are separated from the bulk, and the more the mini bulk is separated from the bulk. So essentially, in the ratio of outliers to bulk appears a quantity which is generalization. So here's a summary. So what I discussed today is a boomlet which happened in the last year in deep learning in measurements of different DeepNet spectra. I showed you a bunch of intriguing patterns which were ubiquitous, appearing everywhere, and which appeared in all the modern DeepNets that I ever looked at. And this structure is caused by the cross-entropy loss, which induces this CC prime two-way structure with replications I. And this index structure is inducing a global mean, which is causing the top outlier, C-class means, which are causing the C-1 outliers, and C-squared cross-class means, which are causing the mini bulk. And I was able to show you how this structure is, first of all, you can justify it somewhat rigorously using the knockout procedure, and you can also see directly in features and backprop errors, and it's inherited by the Fisher information gradients and the Hessian. Also wait. And I would like to say that essentially the takeaway of this lecture is that there's different spectral patterns that can be observed which are emerging due to the two-way layout in the indices, CC prime, which induce the class means and cross-class means. Now, the spectral patterns are simply byproducts. The spectral patterns are not fundamental. You just observe them once the class means are strong enough. But what is the fundamental quantity to be studying are the class means and cross-class means in the features and backprop errors. And so all of these 20-something papers which are looking at the spectrum of the quantities, mostly Hessian, are not studying, in my opinion, the fundamental quantity that should be studied. Thank you very much. questions, Ichao?
Yeah, so I collected some questions from the students.
Okay. It was mentioned that the gradient descent happens in the subspace spanned by the outlier eigenvectors. Does it mean that even a randomly initialized model or initially trained model also has these outlier eigenvalues? How do these outliers develop throughout training is a wonderful question because my next slide shows this. Aha, I predicted this. So the outliers are essentially emerging as function of the training. So initially there would be no outliers, and then once you train more and more, these outliers would separate more and more from the bulk. The way you can see this is here, for instance, if you look at this, here it's very clear. So notice the blue is the bulk, and so here's the bulk. And you can see how there's separation between the bulk and, let's say, the mini bulk, whereas in the beginning of training, there is almost no separation. It's very hard to see here. There's actually a very nice video on YouTube that measures the spectrum throughout the epochs, and you can literally show just outliers emerging from the bulk. Do the observed outliers or this meta pattern indicate anything about data quality, or this is a natural occurrence? I'm not sure what does it mean, data quality. Does anyone want to clarify what is data quantity? Quality, sorry.
Is it due to the data being particularly good for classification by deep nets or particularly bad? Like is there a relationship? And I think the answer would be good.
I can say that I ran experiments, for example, when I tried to scramble the labels. And even in that case, you can see that there is a set of outliers emerging from the bulk on the trained data. So it means that once a network is able to memorize the data, you will get that these outliers emerge from the bulk. But if you were to look at the test data, you would not see that. So
But if you compare MNIST, for example, with SQL, MNIST is an easier data set for classification.
yeah, I don't think that you would get. I know what you're saying. So you're asking, is there some type of monotonicity in terms of the separation of outliers from bulk? I think it's very, very complicated, and I really don't think. Because the most complicated quantity you could study is the Haitian. I think if you look at the features, in that case, you might be able to compare different data sets. And even in that case, you would have to normalize things in a proper manner, which I haven't seen anyone do.
So on this data quality question, so I'll summarize my understanding of what you said to us. Suppose that we were looking at spectra associated with the test incident, and we saw no outlier.
Mm-hmm.
Then without making any measurements, I would just say probably we have lousy generalization and lousy classification performance.
Mm-hmm, mm-hmm,
On the other hand, if I did see outliers
mm-hmm.
on the test Hessian, then like with, eyes closed, I would say, oh, we're doing great on classification performance and also generalization is good.
Mm-hmm, mm-hmm. Exactly. But to make the direct connection between misclassification and the separation of outliers from bulk, I think that's extremely non-trivial. Unless you cheat, which you can always do. For instance, cheating would be, and you can see this everywhere, you take a certain, the question is, what do you measure things as function of, right? If you measure things as function of one axis, you might see that there's gradual separation of outliers from bulk. Now, it would be easy to get that as function of epochs. If you look, for instance, as function of data set, that would be extremely harder, extremely more hard.
Sample size?
Sample size would be much harder. It very much depends on what you're looking at.
So what is so this is a empirical analysis the way you presented it, and you had
think empirical analysis is, it's the disadvantage of empirical analysis is you can find yourself making infinite measurements and coming up with nothing. And I think it's the risk associated with measurements is higher than the risk associated with theory. Because I think if you do theoretical analysis, you'll always be able to squeeze a result. I think it's a lot more interesting once you actually observe a phenomenon in trained networks without making any type of modification to the network. So you can compare this, for instance, to the NTK storyline. So what happened in NTK was that there was the original work that derived the spectrum of the NTK showing that it doesn't change, right? And then what happened after that original work is people said, 1 second, where are the measurements? And so people started making measurements, and then they corrected their initial statement saying, 1 second, the NTK does change if you initialize it in a certain manner. So the initialization is very important. We actually had like 3 lectures, or maybe even 4 in this course, where people said the same statement. NTK regime depends on initialization. And so what does this teach you? It teaches you that if you start by doing a theoretical analysis, you inject assumptions, and then you might find yourself that the assumptions do not hold in real data. If you start with real data, then you start with a phenomenon that is real, and then you go back and you try to find a simple example where the phenomenon still happens, and you try to analyze it mathematically. Does this answer the question in some way or form?
Okay, so the difficulty of theoretical analysis is that you're studying some theoretical sandbox of doubtful relevance. And the difficulty of empirical analysis is that you're getting this overwhelming collection of measurements, and there's just so many questions you could ask about the measurements, and it's so difficult to make all of those measurements cohere to any kind of narrative.
Yeah, I think that's the art. How do you find the narrative in a set of measurements? That's not very easy.
So another thing that we've seen here is that you can publish dozens and dozens of empirical papers where there's stuff visible in the plots, but people don't really point to what they are. They make maybe sporadic mention of some of the phenomena, but they're just sitting there in plain sight.
Mm-hmm.
And there's a lot of that going on with empirical analysis.
I think that's trying to do meta-analysis in deep learning is playing to the strength of this, or to the qualities of this field. So in deep learning, you have infinite amount of research that's happening. And so because there's infinite amount of research, you might try to adjust the way you think about your research to leverage all of this infinite research. Try to gather insights from all the different papers that are appearing everywhere.
So try to explain clusters of papers.
Yeah, exactly. It's like meta-analysis. People do this in, I don't know, biology, right? And this type of disciplines.
Clinical medical research.
Mm-hmm. Yeah.
I'm wondering, so this is more in a like supervised context.
Yeah.
If we're trying to do something unsupervised, would you still see the separation of the spectrum in some cases?
Yeah, so it's kind of harder. There's a very specific reason why I'm studying supervised classification, is because you see an outlier and you can say, I know this is due to class means. In an unsupervised setting, you might see an outlier, but you don't know what it corresponds to. Now, there's actually a recent paper from my PhD university where they study denoising networks, I think, and they show that the top eigenvectors of the Hessian are representing certain low frequency, images, which is something you would see in a bunch of image processing papers. So there's definitely the same type of structure, but it's a lot harder to say anything because you don't have the labels, you don't have a way to assign the top outliers to something.
What if I have the label, but I pretend that I don't?
So
And then trying to go back, if I try to analyze in the unsupervised way, but then to see if this unsupervised approach will discover some of the structure that might be associated.
oh yeah,
with
that's a great idea. Yeah.
But it had,
The question is, what is the optimization problem, or what is the unsupervised task that could allow the discovery of similar structure? Like, how do you find in the Hessian of some unsupervised task some of the same linear subspaces appearing? Yeah, well, you would be feted and celebrated, I think, if you can figure that one out.
Mhm. No more questions. Alan? Yeah.
So, how much of the things we saw here are related to the depth of the network? So, if I have a standard multi-class classifier, which is not necessarily a deep net, would I see similar phenomena?
So if you have a standard classifier, it would depend, again, on how strong are the class means compared to the within-class variation. So for like a linear classifier, you would literally, you can just derive it. It's the class means in the data versus the within-class variations of the data. Fisher LDA. You're asking how much of the phenomenons that were observed in deep nets would appear in a single layer network or zero hidden layer network. So you would see the same phenomenon in the sense that you would see a set of outliers emerge from a bulk, and you would see this mini bulk as well. But the emergence, again, depends on how strong is your class mean versus the noise. So essentially, that's what's derived here. Essentially, how strong are the class means is dictated by T. T is the signal to noise ratio. If T is very large, then you would get emergence and you would get the same spectral patterns and so on.
And does deep net, in deep net, maybe this thing is larger than one layer?
What do you mean by this thing?
The SNR parameter?
Yes, you'd have an SNR per each layer. And what happens is that if you look at this plot, what this plot is showing is that, this plot is that the SNR increases as function of depth. Because in the last layer, you get a very large gap between the class means and the within-class variations, whereas in the first layer, you get very small. So what the network is doing, it's like pushing the class means outside of the noise somehow. I think that's a very big riddle. How does this happening? Okay.
Okay, so again, for those taking the course for credit, there's an assignment due the 15th, the latest, and we hope you've enjoyed the class, and we've certainly found it very interesting to see some of the leaders in this area of research come and give their talks. Thanks again.
Thank you.